Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with the introduction of computational thermodynamics. Before doing the hands-on sessions, we'll cover a couple of more topics. So these are the things we'll cover today about binary Gibbs energy data, the sources of it and the models used, especially the temperature and composition dependencies, how are they modeled. And when it comes to binary models, we will have to do the modeling based on the type of phases. We will see one type of phase, solid solution, how the modeling is done for that. Once that binary Gibbs energy descriptions are introduced, then we will see how higher order Gibbs energy descriptions look. Basically, how to do the extrapolation from the lower order and understand the higher order description. Then we will see how the equilibrium calculation is done in the routines. It's by a method called constraint minimization. We'll see that. So when it comes to the sources, there is no single standard source such as SGTE for pure element. There is no single standard source for binary data. However, binary data are available for a large number of binary systems in different sources. One, open literature, and then data repositories, for example, NIMS, MATNAVI, NIST, etc. Then commercial and open source multi-component databases. This is what we will be using basically when we use the software. The databases that come along with the softwares, we'll use that. They are one of the major sources for binary data. And of course, CalFERD researchers across the globe generate and refine the binary and higher order Gibbs energy descriptions continuously. That keeps happening. Let's understand the models in the binary level. Temperature and composition dependencies of Gibbs energies are modeled generally. Pressure dependency is also modeled depending on the requirement. And modeling depends on the type of phases. We didn't have this problem when it comes to the unary, but in the binary, we have different types of phases. Based on that, we will have different models. And when we see in detail about thermodynamic assessments and models in future, there we will deal about each phase and how the models are used for different phases and things like that. Here, since we are getting to know what is there in the database and how the descriptions look before doing the hands-on sessions, we will start with only one type of phases, that is random solid solutions. So that is here random substitutional solid solution phase SSS, which has no chemical order, and for example copper nickel FCC is a random substitutional solid solution. Now let's look at the model. How is it done? See, Gibbs energy of A, B we have seen in a binary G versus X plot. This is how we start pure element Gibbs energies. The reference energy is here, and from there delta G mix ideal takes the Gibbs energy of a phase ideal solution here, but real solutions may be deviated from that. That is G phi here. Phi is the phase that we are talking about. So G of a phase phi is equal to G reference plus delta G mix ideal plus the excess Gibbs energy term. This is the deviation from delta G mix ideal line. This delta G mix ideal we know is minus T delta S mix ideal, which is calculated by this formula. We have seen that this will be used in CalFERD as well. Delta G mix XS is XA XB LAB. So this is slightly different from what we have seen till now. This is how the excess Gibbs energy of mixing is modeled. This LAB is model parameters, function of temperature and composition. Both are included in this. We will see that how in more detail shortly. And RK power series, Redlich-Kistler power series is used widely in place of this model parameters. We will see that. If you remember in a regular solution, we talked about delta S mix is equal to delta S mix ideal, and delta H mix is omega XA XB, right? So these two things may look similar now. XAXB LAB, here XAXB omega. So in a regular solution, the LAB here is equivalent to the interaction parameter. So in a regular solution, this is so delta GE mix is equal to delta H mix, and LAB is equal to the interaction parameter. Now for any other solution, we have to generalize this. So this is some other solution. Delta GE mix XS is equal to XA XB LAB. This LAB is function of temperature and composition. So you see XA, XB, T all are here. So LAB, so these LAB model parameters represent function of temperature and composition, and they are represented using Redlich-Quistor power series, the temperature dependency. Let's see them in detail. In a rough sense, this part takes care of temperature dependency and this part takes care of composition dependency. Of course, there is this XAXB multiplied here. This is also going to take care of composition dependency. So it's quite complex. We'll break it down and understand. This LAB nu, this term will be usually having this temperature dependency. So V1 plus V2T plus V3T ln T. It's more like A plus BT plus CT ln T kind of a expansion. And instead of ABC, we are using V1, V2, V3 here. And this V1, V2, V3 up to Vn are called coefficients of model parameters. Later, when we do thermodynamic assessment in thermocalc software using Parrot module, we will talk about these model parameters as variables. Anyway, we will see that in detail again later. So these model parameters, how are they useful? Based on this particular phase, let's say delta GE mix XS is like this, because G reference and delta G mix ideal are straightforward, easy to understand. Delta GE mix is the one which is difficult to model. Depending on case to case, it may get quite complex. In this case, it is like this. So you see the curve is quite complex already. How do we model this? So delta GE mix XS is equal to this thing we have written in the previous slide, XAXB summation over 0 to n LAB multiplied by XAXB power nu. So this nu 0 to n is going to repeat and that has to be summed depending on what is n. So depending on the complexity of the curve, we can increase the n. Let's say in this case we need n of 2. LAB values are constant, let's say minus 10, meaning LAB we said V1 plus V2 T plus V3 T ln T and so on, right? So that LAB term, we are keeping it to only one term, V1 let's say, and that is minus 10 here. Okay, so based on this we are going to continue. Let's say starting with, say we have to go nu equal to 0, nu equal to 1 and nu equal to 2 because n is 2, right? So let's start with nu equal to 0. What is that? LAB 0. In place of nu we are going to write 0. LAB 0 is equal to minus 10. We are going to take minus 10 for all the LAB values. We are going to keep minus 10 kilojoules here. Then what will happen to delta GE mix? If LAB 0 is the only term, then it will be XA XB LAB 0 XA minus XB power 0, which is equal to XA XB LAB 0, right? But we are not going to stop with only this. We are going to continue. First, if we substitute LAB being minus 10, we are going to get this term, right? And that is LAB 0 term. For nu equal to 1, we are going to get, again, if you, for nu equal to 1, let's do that again. LAB 1 we need, let's assume that also to be equal to minus 10. Then delta G mix XS will be addition of these two things multiplied by XAXB. So this XAXB is going to come here, multiplied by LAB 0 XA minus XB 0 power 0 plus LAB 1 XA minus XB power 1. So this term we have already seen here, this becoming 1. If we do that here again, so we will get minus 10 minus 10 into XAXB power 1, right? So if we do this, then if we also calculate nu 2 in similar manner and add all the three terms, only then we will get delta GE mix. Pictorially, this is how the LAB 0 will look. It's symmetric. You can see here, this is only the LAB 0 term, XAXB multiplied by a constant value. It's going to look symmetric like this. Then LAB 1, which is multiplied by XA minus XB term is here, right? So that term is going to look like this, and LAB 2 is going to look like this. For LAB 2, XAXB power 2 will come, right? Then it is going to have this kind of shape here, and adding all the three, the green, the yellow and the orange, we will get the white line. That's how delta GE mix is modeled. A symmetric delta GE mix requires only one L parameter, that is LAB 0 for modeling. But more L parameters if we add, They represent more complex composition dependencies such as this. So you can see from left to right, XB is increasing and delta G is varying in a very complex manner depending on the composition. Therefore, we need this many number of L parameters in order to capture that. Right. So when you see a Gibbs energy description, now you can think about how it is broken down into temperature dependency terms, the LAB terms, LAB 0, LAB 1, LAB 2, and for each LAB term we are going to multiply with some XA minus XB power term, XA XB power 0 or XA minus XB power 1 or XA minus XB power 2 and so on, and then all these things are added up. Okay, that's the meaning of this term here, summation term. Different LAB terms multiplied with their composition dependency are added. So in general, this LAB term will not be just a minus 10 value. It will have this kind of a complex temperature dependency, and the coefficients of model parameter V1, V2, V3 all are required. Only for n equal to 0, if I write the generalized form, it's going to look like this: XA XB multiplied by temperature dependency. XA minus XB power 0 is here, so this is 1. What you basically see is XA XB multiplied by a complex temperature dependency term. I'm not showing the screenshots of TDB and all. We will see that as we go along. In the future, we will see more on these models, understanding the terms in models for other types of phases, thermodynamic assessment, how the Gibbs energy description is generated through thermodynamic assessment, and to do that, what are the input data required, thermochemical and phase equilibria data, and how the output, basically the Gibbs energy description, comes. All these things we will see later. Now let's look at higher order Gibbs energy terms, how they come from extrapolation. It's a very important idea. Let's think about a ternary phase in a IJK system, IJK hypothetical system, and this is the composition where we need the Gibbs energy for a phase, let's say. Okay, for example, G of a phase for the equiatomic IJK, all three are equal in amount, composition is needed. Okay, so G of only binary subsystems are available, meaning G in IJ system, JK system and IK system, that is available, meaning if the same phase, for whatever phase we want to figure out the Gibbs energy here, if that phase exists in IJ, JK and IK, we have the Gibbs energies of that phase in the binary sites. So how do we calculate it for the ternary? Ternary G can be obtained by extrapolating the binary using various methods of extrapolation. One method is Redlich-Quistar-Maggianoff scheme. This is widely used one. By default in softwares like Thermocalc, this is used. And how it works is like this. You take the binary compositions here, these three binary compositions, and add them up to get the ternary Gibbs energy description. So this delta G mix XS extrapolated. This is the term we are going to figure out from binary values. LAB is known, LBC is known, LAC is known for a phase. Multiply that with the compositions respectively: XAXB, LAB, XBXC, LBC, XAXC, LAC. This is called as extrapolated excess Gibbs energy of mixing in the ternary phase. And the actual Gibbs energy of mixing of the ternary phase would be this term, extrapolated term, plus a correction term, ternary correction term. Meaning, if you do the extrapolation, you think that you get the ternary data correctly, which will mostly be right, but there will be some deviations. That deviation is captured in the ternary correction term. Okay, so delta G mix is all these three terms plus a ternary. This is the ternary interaction term, Lijk. Okay, Xi, Xj, Xk, all the three mole fractions are multiplied with that. This is how the extrapolation works. This is the generalized form of that in the summation notation. Now, this is an important idea. Diminishing significance of higher order terms. You see, this is the extrapolated, this is the correction term in the extrapolation, right? So, that correction term is this Lijk, the ternary interaction parameter, multiplied by 3 mole fractions. Okay, this is quite important. The ternary correction term is multiplied by 3 mole fraction values. For example, if xi, xj, xk are zero point 0.2, zero point 0.3 and zero point 0.5, multiply all the three, you get 0.03. Think about it. This Lijk, if it is a ternary interaction term and it is, let's say, minus 1000 joules, multiplying that with 3 fractions like this is going to make it 0.03 multiplied by 1000, which is just 30. So minus 1000 has become minus 30. Only minus 30 will be added to this term because of this. Okay. So that's a small contribution. Multiplying the correction term with 0.03 makes its contribution to delta G mix excess very small. Similarly, a quaternary correction term is multiplied by 4 fractions. If at all we do the extrapolation to 4th order, we will see that the 4th order interaction term will be multiplied by 4 fractions and its contribution to delta G mix will be eventually very small. Hence, as the components increase, the higher order terms become increasingly insignificant. This is a very important conclusion. I am going to put it in another slide here and call it as one of the reasons for computational thermodynamics success. Okay. As the components increase, the higher order terms become increasingly insignificant. The unary, binary, and to some extent ternary data are the profound contributors to the Gibbs energy descriptions of higher order phases. This is important. Thus, only the lower order data is often good enough to calculate the behavior of a multi-component system. Meaning, I am talking about real alloys such as, let's say, nickel-based superalloys and all, where we have more than 10 elements. We can predict the phases in that. We can predict the behavior of that system based on only the binary and ternary subsystem data within that multi-component space. Okay, with this we have introduced the basic Gibbs energy description, how it looks, how the TDB file looks and things like that. So the moment we use a database file, now you know what is there in that. Basically the Gibbs energy description, basically the function of Gibbs energy with respect to composition and temperature, right? So with this we are going to look at what happens when we click buttons such as perform now or compute equilibrium in the software. Okay, so equilibrium calculation is what happens there, and it is done by a process called constraint minimization. I will give a small introduction to that now. Calculation of phase equilibria is basically this: chemical potential of an element becoming equal in all the phases or Gibbs energy of the system becoming minimum. These are the criteria we said to achieve phase equilibria. And what basically is done in the calculation is this: identify the set of phases that either minimizes the Gibbs energy or in which the chemical potential of each element is equal across all phases under given conditions. So we know what we are talking about, and this is done in the software. It's called equilibrium calculation through computational tools. If you remember these two Gibbs energy curves, here at one temperature solid is stable throughout, here at another temperature solid is stable only for a small region and liquid is stable only for a small region. Both solid and liquid are stable for a small region, right? Eventually in both the cases we are figuring out this minimum Gibbs energy envelope. This is what we need to calculate when we do the equilibrium calculation, right? So this is called as constraint minimization. So meaning minimize the Gibbs energy at a given pressure and temperature under the constraints of mass balance. What is it basically is, if you think about an example of a business, your input is restricted, right? In the sense that the manpower is restricted, the investment is restricted, so the raw materials are restricted. So within these restrictions you need to maximize your profit, right? So in the business, within certain constraints you are maximizing something, right? Here within certain constraints we have to minimize something. We have to minimize the Gibbs energy under given constraints, that is constraint minimization, right? So number of phases, their fractions should sum up to 1. Weighted summation of composition of each element in each phase should sum up to the overall composition of the component, right? Think about it. If we have certain elements, let's say A, B, C, three elements are there. Percentage of A, percentage of B, percentage of C is there. This is the overall composition. And when we say, let's say two phases are there in this material, and in each phase, A, B, C, all the three elements are there. So there is some phase fraction for two phases, and the composition of each phases are also there. These individual phase compositions weighted by the phase fraction should not violate the overall composition, right? Whatever is the overall composition in your hand, that is the restricting factor now, right? So that is how constraint minimization works. So this is a numerical technique. So when we do the calculation, we need to give some inputs. We say minimize G at given pressure temperature under the constraints of mass balance. We have to tell what is the pressure, what is the temperature, what is the composition, at least for C minus 1 components we have to tell. And size of the system also would be required. And the output is going to be whatever we need: the phase diagram, number of phases, types of phases, fraction of phases, composition of phases, and thermodynamic properties and any related data. All these things can be output. Depending on our requirement, we can extract it out. Thank you. I hope the lecture is useful. See you in the next class.